A set is something that's static. You've got some observables, and these can be anything, absolutely, and they don't have to be organized in any structure whatsoever. That's what a set is. It's a collection of things without a structure. And then the idea is to encode everything we encounter in formal study of science as a set. And it kind of gets boring at some point because you're making everything frozen. And especially for a physicist, you want things to move around. And that's what category theory does. It tells you, let's not begin with sets as the main starting point. Let's begin with functions as the main starting point. So what is a function in the language of sets? Well, it's a way of mapping points from one set to the other. Actually, you can even start with something much more general than a function. You can have a relation. So that would be a way of coupling things from the first set to things in the second set without any rules whatsoever. So the same thing can be coupled to different things. And once certain choice of couplings have been made, we say that we've got a relation from one set to the other. So if this set is called X and that set is called Y, the drawing with the blue arrows defines a relation from X to Y. And in set theory, we describe it as a subset of the Cartesian product because we want to think of every pair of points that get coupled as an ordered pair, which itself can be defined set theoretically as the set consisting of the set of xy and the set of x to distinguish the first component of the ordered pair. And then you think of the R as the set of all such ordered pairs. So xy here would be one element of R. So this notation is familiar to you, Mike, right? Okay. But you see, to define a relation, so there are two problems with this approach. One is that, first of all, to define a relation, you already need to build up some set theory. And second is that the world is not necessarily just relations. I mean, many things can be expressed as relations, but you want to consider maybe real-life situations which are difficult to describe as relations, but you still want to do some mathematics. So what category theory does, it tells you, okay, let's not begin with X as a set of things. Let's begin with X as an abstract entity, so a dot of its own. And then a process that takes us from this, whatever, this state, this universe, this set, whatever we want it to be, to another one is written as an arrow. But now we don't define it anymore. We take it as a starting point.
The arrow or the whole?
The whole thing. The whole thing. So basically, later on, we'll see that a category will consist of the data of dots and arrows. But there is more. When I have two processes, I want to compose them. So this idea of motion, right, comes in here very explicitly. We do think of R as something happening in time, even if it can still model things that take instantaneous time. And when something happens in time, you can make that happen, and then after that, make something else happen. And that's the idea of composition. So it's process R followed by process S. The two processes now seen together as one process. Now, back in set theory, if these are actual relations between sets, the composition is defined using a complex formula. We say that S composed with R equals to the set of ordered pairs XZ, such that, can I erase with this? Oh yeah, that's good. Such that there exists a y for which x, y is in relation R, and y, z is in relation S. And on this set theoretic picture, this will mean that if I now have an S relation, which can be pictured maybe, let's say, with red arrows, the composite of these two relations will trace the arrows and see which elements get paired up by such a trace. So if this is S, and now I want to move from X to Z, I begin at any point here, I follow the blue arrow, and then I get stuck. If I begin at X, I follow the blue arrow, I get stuck with Y. There is no way to go from Y to somewhere in the set Z, so that means that X will not get paired with anything. But if I begin with a different arrow, different blue arrow, let's say, if I started with A that I just put in there, I follow the blue arrow, then I can follow the red arrow in two different ways, actually, and I'll end up with, let's say, B and C. And so then the pairs AB and AC, both of them will end up being elements of the composite relation. So that's how we compose relations set theoretically, and this is the formula that generalizes this principle and detects the set of all such ordered pairs, the ones that we showed on the picture. And you can see that already the formula is complicated. It already brings in logical symbols, or existential quantifier conjunction, which is already a big challenge for students to understand. So this approach, the set theoretic approach, makes it very difficult to talk about processes in abstract. Whereas in category theory, we don't define the composition, we are given the composition. And so it eliminates this layer of complexity immediately. And as I said before, we also want examples which have nothing to do with compositional relations. Okay, so I've tried to set the intuition for how I want to think of dots and arrows in category theory. But now let's define what a category is, which will be a universe inside which we will be traveling through the arrows between various dots. And the axioms of a category are very, very simple and also very algebraic. Okay, so let's see if I can move on by scrolling up. I need to learn how to scroll up first.
I think we do the select on the top left.
This one?
No, just right to it.
Select.
Yeah, and then it should be. Oh no.
Let's see what's happening here. What's this? I guess this was. Sorry, I did something bad.
I think you can add pages.
Okay, this is go to the HTML symbol above them. Yeah. And just go to PC again. This went to like the different.
I see.
And maybe just click on select again to toggle it off. If
Or you want to select this one?
Yeah, I don't think it would be on the left one. It would be on this. It might
maybe
be
here. Yeah,
that's a new page.
Yeah, that's what I wanted. Yeah, thanks. So, Liane and Carlisle, can you see the blank page?
Yes. Yes, I can see it.
Fantastic. Okay, so now I'm thinking whether I want us to look at what a category is first, the definition, or look at examples first.
I'd like to see the axioms.
Okay.
Again, yeah. You just have to do the draw again.
Yeah.
Something like that.
Thanks. Okay, if I do this, then I can erase. No, not anymore. Okay. So maybe in the erase I should switch to white. Okay, sorry, I'm still figuring this out. Okay, now I did everything right. Okay, that's weird. Okay. All right, I'll just give up on that. Just to erase it. So a category consists of. So I'm defining a category now. In mathematics, there is always two ingredients you want to know about a mathematical real: the structure and the axioms. We distinguish between these two. The structure is kind of tells you how something looks like, and the axioms tell you what features it needs to have. For instance, the Earth has a structure of a sphere, more or less, and then everything else that really makes Earth Earth, and not just a general sphere, will be the axioms. So a category consists of objects. These are the dots. And arrows. Well, maybe I don't want to call them arrows right here. I'm going to call them in brackets. So they're more officially, they're called morphisms. Coming from the word morph, and morph means to transform one thing into another. And they're the arrows. And composition of morphisms. Now, the arrows are not just arrows. We have some information about them. Every arrow has a starting point and an ending point. The starting point is an object, and the ending point is an object as well. Morphisms, each having a domain, that's it's an object, and a codomain, which is also an object. Composition of morphism is not defined just for any two random morphisms. It's defined for pairs of morphisms that match up on a certain picture. Defined for pairs of morphisms Fg when the codomain of G matches with the domain of F. So it's a mouthful, so there are pictures we use. As a category is an algebraic structure, but also a geometric one at the same time. And the geometry is very helpful in talking about categories. So the objects, as we already said, there will be dots. And then the morphisms will be arrows on the picture, where the object from which the arrow goes out from will be called the domain of the arrow. And the object where it goes into will be called the codomain. Another terminology for the same thing is source and target. And it's not like we're saying that this domain is a universal domain for all the arrows. Different arrows could possibly have different domains, or the same. That's also possible. So it could be that we have situation where we've got, let's say, two arrows running from one object to another, and then there is an arrow running backwards, and then there's another one going there, and there is one completely isolated there. So if I call these things F, G, H, I, J, then we can see from here, let's say that the domain of I matches with the codomain of G. But there are also other domains and codomains which do not match with each other. Actually, that's exactly what we want in item 3. We want pairs FG so that the codomain of G matches with the domain of F. So in the picture, this would mean that we've got G running from some object to another one, and then F running from that same object to something else.
So when we're saying the pair FG, we're thinking of the rightmost as being applied as the first thing, and then F. So the way that you do function composition.
Exactly. Yeah, that's a good observation. Yeah. To match with function composition, we have this twisted way of writing this. Yeah. So it's defined for these pairs and is denoted by so we write F circle G to represent the composite of the pair FG. Composite is the result of applying composition. We will distinguish between these two terms, and they have to be distinguished by grammar. So composition is the entire operation, it's the circle. Composition is the circle on its own as an operation. And the result of applying the operation to a specific F and G is called the composite, which is a morphism, yeah. On the picture, so it's not just any morphism, its domain and codomain are restricted. So it will have domain the same as that of G, and the codomain the same as that of F. Okay, when I write, you probably can't see what I write, or can you?
Okay.
Okay, good. Because I'm standing in front of it, so I'm not sure. There we go. So let's write this down as well, this information that the composite needs to have certain domain and codomain matching with that of G and F. So we write this to represent the composite of the pair. The codomain of F composed with G must equal the codomain of F
Professor?
Yes.
Chad would like to join the in-person lecture, and he wants to know which room it's in.
We're in the seminar room in the physics building.
Yeah. Okay.
Can he get in the building?
Yes, he can.
Thanks. So the domain of the composite must equal the domain of G. as it is shown on the picture. Hi, yes, please. So what we've done so far is to describe the structure of a category. We haven't stated yet the axioms, even though in some sense some axioms are already included in the structure. With the sphere example, we could have said a sphere, Earth is a shape, and then have the property of the spherical property as an axiom rather than as part of the structure. So you want to have a good taste of what to include as part of the structure and what to include as part of the axioms. And so we included some axioms as part of the structure, so that the axioms become nicely distinguishable from the rest. And there are two of them. But before I move on to the axioms, is the structure clear? So the axioms are first is called associativity. It says that every time, I'm going to be drawing the axioms with pictures. It says that every time I've got three arrows arranged as in this picture. Okay, one remark I should make. When I draw these pictures, it is possible that two of the dots represent the same object. If I knew for sure they do represent the same object, then I would write the arrow as a loop. But I don't know, I want to keep my picture to be general, so I don't write it as a loop, but I don't exclude the possibility that some of the objects here are the same. So when I have three arrows in this arrangement, I could compose G and F, and then compose the result with H on the other side. So then it will be H composed with G composed with F. Or I could first compose H and G, and then compose that with F. And if you think of these three arrows as processes, and let's maybe give an example. So F means putting on a jersey. G means putting on a coat. And H means putting on a hat. Now, if I put on a jersey, that's to F, and then put on the coat and the hat simultaneously, that's the same result as if I first put on jersey and then coat, and then after a while I put on the hat. Composition of processes is associative. So we want these two things to be the same. So these two must equal. By the axiom of associativity. Note, however, that it's not commutative, right? Whether the order in which I put my coat or hat doesn't matter, but it matters when it comes to the jersey and the coat. First put on my jersey and then the coat, the result will be different as first putting on my coat and then the jersey. And the second axiom is the identity axiom, which says that for every object X, there will always exist an arrow going from X to X, which will have a special property. The property is, so this arrow is called the identity arrow for the object X, or of the object X. And the property is that it behaves like 1 for multiplication. If composition was multiplication, this would be number 1. So I've got here G, I've got here F, and the rule says that G composed with identity of X must equal G, and identity of X composed with F must equal F, and this must happen for every F in G. Identity of X is unique for each X. It's the same for each, not just for X, but for each F, G, and so on. So this thing doesn't depend on the F. It's not that every F has its own identity. It's a universal identity for all the Fs. It can actually be proved very easily that you can only have one arrow having this property. You cannot have 2 different identities. And the proof goes like this. Imagine you had another one.
The second one, if you have the F composed with X, if you apply F, aren't you at X? Oh, or okay, no, it's the same morphism. Okay, no,
Yeah.
no.
So
it's just the.
It's a good question, though. Let me actually draw a picture for that. So according to our rule of composition, if F goes from W to X, identity going from X to X, and G going from X to Y, the composite of F and identity must go from W to X, and F does, so it's valid to say that they could be equal. And also here, we want these to be equal. When I draw this equality between 2 strings of arrows that are parallel, I mean that the composite of one string equals the composite of the other. In the other case, we just have a single. So why is it that there will be only one identity? If I have another one, what's going to happen? Any ideas? Yes, you want to say something?
Just asking. Sorry, it's my own fault. I missed the first part of the board. But would X be a morphism?
X is an object, but one X is a morphism.
Okay, that would be because there's only one identity map for any given set. So
but these are not sets anymore. These are abstract things. The only thing we know about them is that composition is associative.
Well, there's only one way to do nothing to something, and that's
well, that's a good intuition. That's a good intuition. There's only one way to do nothing to something, but let's prove that there's only one way to do nothing to something. Suppose there was another way to do nothing. Why would they have to be equal to each other? So it's a little riddle we want to solve now. What would happen if I had a second identity?
I guess you construct another Ix prime, and then you compose that X with Ix and X with Ix prime. Both of them should be Ix. Or
okay, so Matt has some ideas on this. Matt, would you like to come and share your ideas with us?
let's see if I can think it through.
You need to select which, yeah.
Okay. Let me just have an object, and I have Ix, and maybe I say there's another Ix prime. Maybe I'm gonna need another object, Y and F. So let me say F composed with Ix equals F X prime equals, should also equal F. And I feel like I should be able to use this. Do I have enough rules?
Well, we don't have the ability to cancel.
I don't have
it,
an
right?
inverse, yeah,
Not every process can be cancelled.
yeah, that's true.
If you burn down the university, you can't cancel that.
Okay. Okay, maybe not this way then. Isn't I x proposed with I x prime equals I x, but also I x prime? Well, again, I'm gonna want to cancel things. Or is this along the right track?
That's what I was thinking.
Okay, it's interesting, yeah.
Proposed with I x equals. I can say this should equals ix or it should equal ix prime. You'd have both. Let's make this a prime. And doesn't that say it?
Yeah, I think so.
Yeah.
Yeah.
Okay.
Thank you. So if I may rearrange the order of this, so ix must equal ix composed with I prime x, because I prime is an identity, but because i's identities also must equal I prime x, and hence making ix and I prime x equal to each other. So everything is actually happening locally around x. We don't even need any other arrows outside of x. Maybe it's worth noting that locally around x, if I only consider arrows that loop from x to itself, so that has identity x, but possibly also other arrows. What do I guess? Now I can compose any two of them because they will always match with the picture that I require for composition to be defined, right? We will always have that f and g are such that the codomain of f matches with the domain of g, because all of the arrows here are from x to x. So I will be able to multiply any two of them. This multiplication is associative, and it has an identity element. There is a name for such a mathematical structure. It's called a monoid.
Let's say G would be distinguishable from the identity, that it doesn't all end up being the same arrow.
Yes, it will be. Yes. Not that yeah, so identity is not necessarily the only looping arrow. There will be other looping arrows. So this is how we write it. Hom is usually used. Hom is a short form for homomorphism. Morphism is also a short form for homomorphism. So because of some examples of categories where morphisms become actual homomorphisms of mathematical structures, we use hom to represent the set of arrows from one object to another. In this case, it's going to be x and x, and we are saying that this thing, hom xx, is a monoid under composition and the identity element. For each x. Now, the reason why I brought this up is because we know, so those who work with monoids, they know that in a monoid you only have one identity element, and the proof is exactly the same.
So is the monoid, sorry, maybe you want to go first.
I think you might be wanting to ask at least a similar question to me. So, well, first I had a question: is homo is the same as endo, right? So is the homomorphism the same as the endomorphism?
Well, endomorphism of x. So another way of writing this would be end x. Endomorphism of x is a homomorphism from x to x.
Okay. And then I wanted to see if I remember correctly, monoid, if I remember correctly, is a magma with inverse.
No, that's a group.
Okay.
When you have associativity plus inverses, that you get a group. Monoid is when you don't have. Think of matrices, n-band matrices. Not every matrix is an inverse, but it's associative and there is identity matrix. You can multiply any two n by n matrices when n is fixed. So that's monoid.
Wait, you don't need inverses then, so yeah.
No, you don't. Yeah, and in fact,
is it just So just identity and associativity.
Yeah, yeah. And in fact, matrices maybe should be our first example of a category.
And then, but then like what you were saying was magma then? Is that
Magma is when you don't have associativity.
it's just
And you
like-
don't have identity either. So it's just
But
when
you
you have a
have-
binary operation.
Okay.
That's why it's called magma. It's very uncontrolled.
Do you know, I've heard monoid being used in computer science a lot, but I don't know how it relates. I don't know if you know.
It is used a lot in computer science in various different ways. It comes from processes again. There is a theory called the automata theory, which is basically a theory of monoids in some sense. You have a monoid acting on your machine, on your automaton. And it's usually the monoid of words. Well, actually a submonoid of it. So the elements of that monoid are words, sequences of letters. And you compose words by concatenating with each other, yeah.
For what it's worth, because we kind of on the conversation you brought up computer science. I know in Haskell a big like question among newbies is what is a monad?
Monad is an upgraded version of a monoid. It needs a bit more category theory to define what a monad is.
Right, I suppose hence why the joke. It's a complex thing. You need to understand Haskell in the first place.
Yeah. Okay, so this was just a side remark to note that in the axioms of a category, when we say that every object must have this identity arrow, having these properties actually uniquely determine Cauchy arrow. So it didn't have to be, I mean, this could have been part of the structure to specify the arrow, but we don't have to specify it because it's always unique when it exists. So we put it under an axiom.
Yeah, maybe one more thing on the side remark of the monoid. So if you only have one object with like the multiple arrows, then you have a monoid.
Yeah.
Okay. It's not like you need to consider the homomorphism of X with itself, or that it is defined as that.
So a category which has only one object
Yeah.
will be monoid.
Even what's the category of one object and just the identity arrow?
That would be called a trivial monoid.
Okay.
Only one element in it,
Okay.
the identity arrows. So let's go back to the definition just to summarize it. So a category consists of objects. We display these objects as dots. There are morphisms. We think of these as processes that take place from one state to another. The process then needs to have a source and a target, or a domain and codomain, in other words. Composition of morphisms, so these processes can be combined in a sequence. And but composition is only defined when F and G are arranged in this way, where codomain of G matches with the domain of F. And then the domain of the composite matches with the domain of G, and the codomain matches with the codomain of F. So just as on the picture. So that's what a category is as a structure. And the properties it needs to have is that the composition needs to be associative every time F, G, and H are arranged in such a way, which is what enables us to compose them the way they are in these expressions. These two different ways of composing them must equal. And every object needs to have an arrow, which now we know will be unique, such that this arrow composed with any other arrow gives back that arrow on one or the other side. So any information that can be described in these terms is a category. Now, what are examples of categories? Well, examples of categories are quite a lot. Almost everything can be turned in a category.
Yeah, can put it as a category.
Yeah, so probably not. You can always turn something into a category. What are important examples of categories? Who knows? One example that is unimportant today might turn out to be important tomorrow. But something that we definitely know already today that is very important is the category of matrices. Because a lot of applications of mathematics takes place in this category. So let's describe it. we will write it as matter, and we will put a subscript here to be the field or the ring in which entries of the matrix come from. In this example, we will be focusing on real numbers, but we could have had here complex numbers. Maybe actually for physics, complex numbers is even more interesting than real numbers. Let's actually do that.
I don't know about interesting, definitely required though.
Yeah.
Sorry?
I don't know about interesting, but definitely required.
Okay. So matrices with entries being complex numbers, but this could have been any other ring as well. It didn't have to be a field. We could have had, for instance, Z12 here. Entries are times
So ring, that's like there's multiplication and addition.
But so that can be any ring, it doesn't need to be a field.
Doesn't have to be a field, no.
So you can have a notion of a matrix without a notion of a vector space.
Yeah, and then vector space becomes a module over the ring.
Okay, I don't know what modulus is there, I guess.
Some of you might have heard of near vector spaces because that's something that is championed in university by Professor Howell. And so near vector spaces turn out to be special kinds of modules. This is actually something we proved together with Dr. Marquez and our joint master student who's now PhD student, Daniela Moore. So near vector spaces are generalizations of vector spaces, but you can actually view them as modules for a special type of a ring.
So just to, is every vector space a module, but not every module is a
Yeah.
vector space?
Yeah. Z modules are important. Z is the ring of integers. Then a Z module is just an abelian group. Plus, it has inverses, associative, and identity element. The modules are very powerful notions because they bring vector spaces and abelian groups under one framework. So we could have had any ring here, but for the sake of the example, let's look at complex numbers. In this example of a category, objects are natural numbers. They represent dimensions of the matrix. Zero, 1, 2, 3, 4, and so on. I include 0 as well because zero-dimensional space is important. What are morphisms? So remember, a morphism needs to have a domain and a codomain. In this case, they are numbers. So if we have numbers n and m, a morphism from n to m will be an m by n matrix. With entries from C. This is not a very alien concept because, as you know, matrices encode linear transformations, linear maps. You already did that in the second year. And so you can think of a matrix, an n by n matrix, as a linear map from an n-dimensional space to an n-dimensional space. And that's what actually we're doing here. We're just not worrying what the vectors inside the space are. And then later on, category theory tells you actually don't need to worry about that because a lot of times all of the information of the vector space is captured by the, not the vector space, sorry, but your mathematical structures in general, captured by the process between them. At least all information that is relevant in a given context.
I have a question about the objects. Do those represent, like you said, dimensions? So would 1 be a vector, 2 be a matrix, 3 be like a order 3 tensor, or is it a different kind of notion of dimension?
They are numbers. They're just numbers.
Okay.
You can also think of them, you can think of n as n-dimensional space, but we pick one space for each dimension.
Okay.
You can think of it as c to the power n. And then you can think of that as linear map from. So what about composition of morphisms? Well, that will be multiplication of matrices. As you know, if we have an m by n matrix A and a k by m matrix B, they multiply. And in fact, the rule of multiplication of matrices, when two matrices multiply, is exactly this rule of matching of dimensionality. That codomain of A must match with the domain of B. So if A is so BA is defined once B is an m by n matrix, and sorry, I think in my notation I've got them k by m. And A is m by n. So in this case, composition becomes the usual matrix multiplication in this example at least. We need to check that the axioms hold. Now that's easy. We already know matrix multiplication is associative, and we already know that we have identity matrices for each dimension. We have matrices with ones in the diagonal and zeros everywhere else. So let's look at another example, which keeps the same objects, but will change the arrows. By the way, if you're wondering, how does this category know about vectors? The answer is easy. You can think of a vector as a matrix where one of the dimensions is 1. You take number 1 and you consider arrows from 1 to n. And you can then we can think of these as vectors. If we think of these as vectors, then matrix multiplication does become linear. They do become linear maps, because if I take a matrix here, A, I multiply NA by a vector K, the result will be matrix AK, which will be exactly the vector I get by applying this linear map to the vector K. Is it something you know?
I'm still trying to see the connection with the object. So K is our vector.
K, remember K is an n by 1 matrix. So it has one column.
Yeah.
So that's how it's vector.
Yeah.
Now when I multiply that vector by matrix A, what do I get?
You get another vector.
Yeah, I get another vector. Yeah,
That's it. Yeah.
and that's exactly the vector. If I think of A as a linear map from an n-dimensional space to n-dimensional space, how do I think of A as a linear map? The basis vectors of my space go to the columns of my matrix. Then applying this linear map to vector K is exactly multiplying A with K, where K is seen as a column vector.
What was the one? I'm still confused on the object.
This is number 1.
Yeah, but what is it?
It's so I'm mind blown that it works, but if I'm understanding correctly, we're thinking of a vector as a map from a one-dimensional space to an n-dimensional space. that's weird to think of a vector as a map.
So in this, even though our objects were abstract, we still have vectors there. Now we have them as arrows. You might ask, what makes, I mean, you might ask, okay, what about one? I mean, how do we access it in a general category? If we had a general category, what would play the role of one? And that's a big question. And sometimes the answer to this question is, we don't have a specific one. Any object can act as one in some sense. Okay. But that's something we'll come back to that later. In this category, we have a nice object, one.
But 1 year sorry.
Okay, so I just want to make sure are the loops from one to itself, are those the scalars in the complex numbers? Okay.
That's right. That's right. Yes. So not just we have vectors, we even have the complex numbers. The complex numbers will be loops from one to itself.
So where is the 0?
Well, I'm just thinking now, is the map from any of those objects to 0 the null that relates to a null space at all?
Well, 0 would be arrows to 0 would be matrices that have dimension 0 in either rows or columns, right? And there is only one such matrix always. It's the empty matrix. So you will always have unique arrow to and from 0 to any other object.
Oh, how do you go from the 0 matrix to another matrix? I can see how you can go into it, but not how you can go out.
Okay, let's talk about this in more detail. So in describing this category, we should have paid a bit more attention to 0 because it's weird to have a matrix with dimension 0. So if I have objects, numbers A and B, let's learn how to describe arrows to and from 0. And also what's going to happen if I take an arrow to 0 and then compose it with another arrow from 0. What kind of matrix are we going to get here?
Anyone you want. I don't know.
That must be a unique answer, right? So I'm going to put an exclamation mark here, meaning that there is only one arrow going to 0. That's matrix which is a 0 by n matrix. In order to understand mathematically what is this, we need to go back to the definition of matrix. When we say m by n matrix, what do we mean by that? What is an m by n matrix? Well, it's an array, right? There are placeholders, and in each placeholder there is a number. So let's look at the set of placeholders, which will be the Cartesian product of an m-element set and an n-element set. This is the set of placeholders. Every placeholder has two coordinates, the row index and the column index. So, for instance, 1, 3 is there. And now a matrix tells us what is the entry at that place. So, and it must give us an entry for each placeholder. We cannot have blank placeholders. So it's actually a mapping, a function from here to the field of complex numbers. That's what a matrix is.
Yeah, because this is without the notion of a vector space. You're not thinking about mapping from one vector space to another because you can work with like modules, general nouns. You're getting to that.
What are you asking about? Sorry, I didn't get that question.
Yeah, yes. Like if I were to define a matrix, I would have gone like from you have a map, a linear transformation or an operator from one vector space to another. But we're not constrained to vector space.
So that definition, that definition is the semantics of a matrix. That's what a matrix does.
Yeah.
It maps a vector space. But syntactically, what it is, it's a data of numbers.
Yeah.
And so we are now defining the syntactic structure. So what happens when one of these numbers is 0? Well, we have to then figure out what do we mean by a set from 1 to 0. There are no numbers between 1 and 0. So this set will be the empty set. So here you'll have the empty set, because empty set Cartesian product with another set is still empty. Since there are no elements here, there's no pair to choose. So we'll have a map from the empty set to C. There's only one map from the empty set to any other set. Because what is a map? It's a set of ordered pairs again. And so it's going to be empty again. So that's what this arrow is, and also this will be the empty set. So there are only unique ones there. But the composite of those two is no longer empty. So let's recall the definition of composition of matrices in general. If I have two matrices, A and B, how do they multiply? If I write b's, small b's for the entries of B and small a's for the entries of A, the BA will give me sums, right? It will be sums of what? One index goes through row, another goes through column. So it will be okay. So which one goes where? Yeah.
If you're going over the columns B and then over the rows. So if you have Bij.
Let's agree on how we multiply matrices first. So if this is B and this is A.
Yeah, you take the first row of B.
Yeah, don't we go like this? Don't we do like this? Yeah.
Dot product each row with each column.
Yeah. So this is where the second index varies in B, and that's where the first index varies in A. So Ij, Jk, where the summation is over J, and then it's matrix of I and K varying in various dimensions that they belong. Yeah. Now, the case where we have A being and a 0 by n matrix, and B, so this is our A, and B being m by 0 matrix. So remember that now this is 0, and so the width is 0 and the height is 0 here. And that's exactly where J must run through. So, but there is no J there. This is the empty sum. What happens if you add nothing to each other? What number do you get? Yeah. If you multiply nothing with each other, you get 1. That's why 0 factorial is 1. Whatever operation you have, if you apply it to nothing, you get the identity element of that operation. Multiplying nothing gives 1. Multiplying, adding nothing gives 0.
Is this constrained to your dot product being, or your inner product being a function like that sums? Like if you had, I don't know if you could have an inner product that didn't have like a sum in between, maybe it was just multiplying the elements, would that then be a different item?
Well, usually when it's not a sum, it's usually an integral.
Yeah,
And then it's still 0. It's an integral from 0 to 0 is 0.
Well, an integral basically is just the whole thing.
It's a continuous sum. Yeah, but then it's still reduced to 0.
But so you can have, because I don't know, you can have an inner product that's not.
If it's a given by multiplication, and included 1, not 0.
Okay.
So Lian and Carlisle, are you also fine with what we're talking about here?
Yeah, I'm still good.
Yes, sir.
So we get a matrix whose entries are zeros. We get a zero matrix.
I have a bit more of a fundamental question. When we talk about map, we have a very similar notion of what a function is, right? How can you have a well-defined map from a set with n entries to a set with no entries?
We don't.
Okay, so then what would
This is not a, you remember, this is not a map.
okay?
It's a map in a different way. It's a map from this set to C. It's a map from the empty set to, it's not a map from something to empty set.
Okay.
Zero is not the empty set. Zero-dimensional space is not empty. It has something in it. There's one point in it.
Okay.
Yeah.
Okay.
And if this is our C to the power n, and this is a single point space, this linear map maps everything to that unique point, which is the zero vector of that space. And this maps the zero vector to the zero vector here. So all the vectors here are mapping to the zero vector, and exactly the zero matrix that achieves that.
Okay, and would the zero vector of the zero-dimensional space be the empty set?
You can define it in any way you like.
Okay.
But yeah, I mean, wait, so yeah, from this approach of defining a vector as a mapping from 1 to n to C, yes, because then this will be empty set and this will be the empty map. So.
Okay, so then the map from n to 0 would be the map where you map everything to the empty set.
Yeah.
Okay.
Yeah. If I think of this as a map between vector space. I want to make a little diversion, just a short one. I was very fascinated to figure out how category theory explains what Brian cats are in physics.
What? Oh, rocket. Okay.
So when you have a vector, so to give a linear map from here to there is to give a vector, because, sorry, this should be C to the power 1. This is a one-dimensional space, right? The linear map is determined where the identity element is mapped to. So it's a single vector, but also this one. So if I have a vector V, I can think of it as a map in two different ways. One is as a map going that way, the other is as going map going the other way. And that is the Brian-Kepler rotation.
It's like related to the dual, right?
Yeah. So is it, I think it's this, right?
That's a row. That's a row.
The function be okay.
No, something, no, yeah.
So the way that I normally know if I remember it right is if when the arrows are on the outside, it gives me a dot product.
Yeah, because if I write this as a composition, let's say this was another one, right? I want to get a number.
Yeah. Yeah, so that's normally how I know if I
composed
remember it right.
Yeah, you're right. Yeah,
Yeah, that's good.
this
And then
composed
the
with
other
that.
way is your matrix.
Yeah. This composed with that will be an arrow from 1 to 1, and then we agree that's the numbers.
So maybe you can give me a small physics lesson. How are Brassenkets any different from our normal vectors?
Well, as much as
Are there just a notational difference, or is there a more mathematical difference?
is there a difference between up and down? Well, no, but yes, because once you fix one direction, then the other becomes the other one. So the directions are different on these two arrows.
I was more meaning is there, are they literally just a different way of writing vectors, or are they actually special vectors in any
No, they're different arrows in the category of matrices.
Yeah.
So they are different from each other.
Yeah. But yeah, and also the brackets, because you start defining operators as sums of like outer products, get products. When you like diagonalize a matrix, it is mostly notational, but like it's a very nice representation because usually your gets is an orthonormal basis. So those that around the head would form a orthonormal basis from like a n by what to m. And so then when you multiply with a vector and you see that sum, it's literally like the brass just catching all the basis vectors that correspond. So then like it's a very nice representation in that sense, but the annotational. Yeah.
Okay, so we now know how to deal with 0 and what are arrows going in and out of 0. So we clarified that point, and we also answered the question you had that led us to this slide, right? I forgot what the question was, but maybe it was.
Yeah, I also forgot the question, but I think we answered it.
So back to the previous slide where we described the category of matrices. It would be interesting exercise or investigation to take various pieces of linear algebra, maybe the one that's interesting and relevant to various applications, and describe it in the language of this category. Quantum story told in the language of a category like this, a bit more bigger category where objects are not just vector spaces but Hilbert spaces, has been described. You can read it up on the internet. We can also have one session dedicated to that. There is a blog by someone called John Byers. He's actually a physicist who is working in category theory, or rather applying category theory to physics. And he has a very nice blog where he tells the story of how we can conceptualize quantum mechanics, if I'm using the right terms, in the language of the category of Hilbert spaces. That's where I learned about this Briar-Cat story. Then I also want to mention a very recent paper by Chris Hennen, an English mathematician, who gives an axiomatic description of the category of Hilbert spaces. So instead of saying the objects are Hilbert spaces, the arrows, blah, 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 you begin with the notion of a category and put additional axioms so that it's forced to become the category of Hilbert spaces. It's a very interesting work. And you can think of this as a kind of axiomatic approach to quantum physics. There are, however, some missing links to be still completed. One place where category theory is already being used in quantum story is things like ZF calculus, which
quantum computing,
which the quantum group is familiar with.
And also, like, it's very big on, I think, with tensor networks.
Right.
Yeah, which is also quantum many-body physics. So.
Right. So at the moment, I think it's so the state of the art at the moment, if I'm not mistaken, is that the categorical story gives you a nice language in which to do computations. But it's not like it's not necessarily that there is a deep theory of categories that you can now suddenly apply to physics where you suddenly get magic answers to open problems.
If I'm not mistaken, what I've understood is it just takes away the headaches that it makes the headaches that we already had less headachy, or they don't really tell us anything new. Right? So
it transforms the language and makes it more accessible and more organized and more rigorous, which is already an important step. And there are a few books written on this. One of them is, one of the very recent ones is Bob Koech's Quantum in Pictures. And you were at that workshop in Italy, right?
Where you gave it to us.
So you've got that book?
Yeah.
Okay, maybe next time, because we haven't seen it, next time you can maybe bring it and we can see what's going on in the books.
Yeah.
In the YouTube video that I saw, he says that he, in this book, he explains very abstract mathematics and its category theory using these pictures. That's the nice aspect of it.
It's very nice. I think he wanted to like give the book to a bunch of high school students. I don't know if you saw that part, and then but then give them, like, take one of the Oxford quantum mechanical tests, convert the test into this like ZX calculus language and the like just diagram language, and then see how the undergrads do and how the high school students do. Where the high school students was just taught the diagrammatic way. So we should still see the results of it. That should be very interesting.
Okay. Yeah. Sure. Yeah.
Easier to learn or reason.
By the way, talking about the language aspect of mathematics, you should be careful not to underestimate its power, because what this ChatGPT, it just knows the language, nothing else, and it's able to prove theorems just by probability of what the language suggests. So there is a big secret hiding there, that it is very much possible that much of our ability to understand the universe and to reason actually is a derivative of the language we use. And if one looks at from this perspective, then the fact that what I said earlier, it's not like there is a big theory that can be applied to solve problems. The fact that there is a nice language in which we can formalize physics is already quite a big thing. But this is something we still need to understand better, in what role language has in mathematics and its applications. Okay, so that was one example, and we will be coming back to this example. I think it will be interesting to come back to this in many different ways. Maybe one thing I want to say now is to actually, I don't know, what do you think? Which direction should we go? So there are two possible directions. So one is to move to another example. And the other direction is to explain the sum of numbers, how dimensions add in the language of arrows. Which one should we take? Are you interested to see another example, or
what would the other example be about?
Well, okay. So if you are wanting to get into the dimensional approach, maybe at an endpoint, what is a tensor product?
So that's a very interesting question. You cannot define a tensor product. You need to introduce it axiomatically. You can define a tensor product, but you cannot define it just.
It would be an accident.
You cannot define it just using the language of the category of matrices. There is a very nice way to define a tensor product using categories. It's called a universal property, but it requires two different categories. One category isn't enough.
Okay.
So this category has tensor product, but also it has addition. By the way, what happens if I take an n-dimensional space and I take its tensor product with n-dimensional space?
Yeah, n by n.
That is multiplication, yeah.
But if you have a basis in the n-dimensional space and a basis in the n-dimensional space, and you tensor product, like the pairs of the basis, that's a basis in the n by n tensor.
Yeah. So tensor product here will capture multiplication, but there is something else that captures addition. And in the other example, that thing that captures addition will also, in a kind of dual way, capture multiplication. So here is another example. in this example, objects are going to be the same as in the previous one. They are natural numbers, 0, 1, 2, 3, and so on. And morphisms are no longer linear maps from an n-dimensional space to n-dimensional space. They're much more primitive entities. They are maps from n-element set to n-element set. Let me actually write this properly. So a morphism from n to m, f, will be a function from the set of n elements, specifically the set of numbers from 1 to n, to the set of numbers from 1 to m.
So it maps sets to other sets. So
Yeah.
mapping elements in the set to elements. Like
That's right, yeah. If the previous category is the appropriate place where you want to do physics or linear algebra and this kind of things, this is your category for number theory. We will now see that addition and multiplication, which are the two important ingredients of number theory, all number theory actually rests on those, will actually be categorical concepts defined through this category. What about composition of morphisms? Well, that's the usual composition of functions. So if I have a setup like this, so I'm not describing composition. This is the usual composite of functions, which as we know, is computed like this. So its value at x is given by applying a p of f of x. Again, I'm not going to go to the axioms because we already know they are valid. It's obvious. So associativity of composition, I think we're all familiar with. And identity arrow for each n will be the identity function. Okay, so I'm now going to do what I promised you I would do. How do we define addition and multiplication of natural numbers by seeing them as objects in this category? This category, actually, we can write it as the category of natural numbers. Maybe nat would be more suggestive of the fact that we are not just thinking of the set of natural numbers, but the entire category of natural numbers. Let's say I've got two numbers and I want to do two different things to it. On one hand, I want to add them. On the other hand, I want to multiply them. When you work in a category, everything is determined by the behavior of arrows. So we're going to pick some random object k and look at the relationship between k and these other objects. Philosophically, you can think of this as how does k see what's going on in n, what's going on in m, and what's going on in the n plus n. And k sees that by signals that it receives from n and m. Let's do a primitive thing first. How many signals will there be from n to k? So what is the cardinality of this Hom set nk? Remember, Hom represents the set of arrows from one object to another. How many functions are there from an n element set to a k element set?
Is it just k to the n?
Yes, and the reason for that is that if I want to set up a function, I need to pick an element here and then decide where to map it to. There are k choices. Let's record that. For the next element, there is another k choices, and then the choices multiply. We agree on the fact that choices multiply. So eventually, we'll get as many product of k with itself as we had number of elements to choose where they should be mapped. So it's k to the power n. What about the home set of mk? Well, that's going to be k to the power m. Now, what about the home set of n plus m to k? Well, that's k to the power n plus m, right? But now we notice an interesting relationship between these three numbers. K to the power n multiplied by k to the power m is equal k to the power n plus m, isn't it? This is a numerical relationship. Is there maybe a deeper set theoretic relationship between these three sets? Number-wise, this times that equals that. But what about set-wise? Well, what is an abstraction of multiplication for sets? Is Cartesian product, right? So what happens if I take Cartesian product of that and that? Well, maybe I get a set that's bijective to that. What would that mean? That would mean that every f and g here has a unique arrow here, which we can think of as fg, as a pair, as an ordered pair. Okay, to decide this, let's unpack what n and m are. So n is a set of numbers from 1 to n. M is a set of numbers from 1 to m. What about n plus m? It's the set of numbers from 1, it goes all the way to n, and then it continues going, right? All the way to n plus m. So is there a way I can think of functions from n plus m to k as pairs of functions from n to k and m to k?
Just add them like element wise.
So maybe let's use more primitive language. Let's say there are, as an example, let's say our n is 3. 3 equals n. Then we have 3 entities here. And let's say our m is 4. Then we have 4 entities there. How many entities do we have in the sum? Well, that's 7. And maybe I'm going to use different color. So the 7, how do we get 7? I mean, what is the set theoretic operation behind addition? We put sets together. Huh? 3 come from one set and 4 come from the other. So the red ones and the blue ones.
Disjoint union.
Yeah, disjoint union. Now I need to describe a function from a set which has elements of 2 colors, red and blue. So I need to say how the function ends on the red part and how the function ends on the blue part. But that's exactly specifying a f and a g. So what I'm trying to say is that a function going out from here, from this domain, can indeed be seen as an ordered pair of functions. One going out from that domain, the other going out from the other domain. And it's actually a one-to-one correspondence. Any function from this set breaks up into function from this set and a function from that set. And these two functions have nothing to do with each other. So there is a bijection between the Cartesian product of these two Hom sets and that Hom set that's underlying this equality of numbers. Let's actually write this down. So Hom NK, Cartesian product with Hom MK gives a set that's bijective to Hom n plus MK. It's not just a random arbitrary bijection. It's some kind of methodological bijection. There is a way to recover f and g out of this pair f g. And in fact, that way is through composition functions. How can I, once I set up a function on this bigger domain, right? How do I recover its values on the red dots? Well, the secret is, and who would like to complete my sentence? Is there a way to link this arrow with the other two arrows by means of some additional arrows we might want to draw in and making use of composition of functions? So we're going to turn this observation into a very important category theoretic concept. And to do that, we need to use the language of categories, which is composition. We're going to decode this bijection in the language of composition. But we have too few arrows, right? Arrows compose when they're one after the other. They're not one after the other. So we need to bring in more arrows. How to do that?
So I'm guessing you need arrows that goes from K to M and K to N.
Backwards. Is there some quotient we could define?
Quotient.
What are the inclusion ones?
Yes. Yes, Kerry. So
From N to N plus M.
right.
and N
Well
to-
done. Yeah. So we've got a map here, a natural one which maps red dots from here to there. We can call it iota 1. And we also have a map there, a function iota 2. It maps the blue dots to the blue dots. But now, magically, if I take any map here, let's call a map here some H, right? If I take a map H, I could map it backwards. Out of H, I can design two maps on the left side, on the right side, just by composing with iota 1 and iota 2. This would be simply looking at what H does to the red dots, that would be my composite on this side, and what H does to the blue dots, which will be my composite on the other side. So from H, I can design a pair of maps. H composed with iota 1 and H composed with iota 2. This specific map now that maps H to those composites is actually the bijection we've got here. It is this that's bijective. If I've got two different maps, two different versions of H, right? They act the same way on the red part and the blue part. They will be the same map. So that's injectivity of the thing. Two different things mapping the same place here will be the same there. And surjectivity we already proved. If I start with F and G, there will always be an H. So this map is a bijection. Now we're going to turn an observation about real life, which is the fact that this map is a bijection, into an abstract concept that will have applications in many other areas of life, not just this one. Okay, so this is now a very interesting point where you take, how do you take something that you observe and extract from it a notion in category theory? We now want, yes?
Sorry, Professor, I just want to ask, so it seems like from this picture we can sort of describe this existence of the bijection. We can describe the one way by saying F can be written as this composition, but it doesn't seem like we can write H as a composition of just the things we have here. So do we need some additional structure to describe that the F and G also gives us an H?
Well, the answer to your question lies in what we drew on this corner, where we said that we've got this mapping. And to describe this mapping, all we need is just iota 1 and iota 2, because the mapping, what mapping does, it maps H to those composites of H and iota 1 and H and iota 2. And now we want this mapping to be a bijection, and that we can state in a general category, because we've now turned our arrows into sets, and we just have a function between sets which we can claim to be a bijection. So we don't actually need extra structure. But what is the ingredient? Because here, n plus m was a specific number we knew about in advance. In a general category, we will not know what this is. What else will we not know? We will not know what iota 1 is. We will not know what iota 2 is. Everything that we will not know in general should now become part of our structure that we define. So the sum of two objects in a general category will be not just a third object, but the entire entire diagram consisting of that third object together with arrows linking the initial objects with the third object. And the condition that this diagram needs to satisfy is that this function, the function of mapping H to those composites, a pair of composites, must be bijection. But there is another way to say that. To say that this is a bijection is the same as to say the following. For every F from N to K and G from M to K, there exists unique H from N plus M to K, such that F equals H composed with iota 1 and G equals H composed with iota 2. Let's go back to our function. When I have a function from one set to another, what does it mean for it to be a bijection? If you think carefully, it actually means that for every element here, there is a unique element there that maps it. That's what a bijection is, once you already know it's a function. We already know this thing is a function in any category because given H, I can uniquely describe F and G just by these composites. So we do have such a function in a general category. And now we want to say it's a bijection. In other words, for any possible thing here, which will be a pair F and G, there exists unique H that maps to it. Mapping to it means that this equality is whole.
So that's like an added on rule, or that we add that to our structure, the purple box.
Yeah, that's the axiom.
But is there a way that we could have added that diagrammatically? Or
yeah, so we're going to say that these equalities can be expressed by saying that these triangles commute. So this string of composite, this composite must equal that, which is to say that this diagram commutes. And the other equality is to say this diagram commutes. Then the condition becomes that for every f and g there is unique h, which makes these two triangles commute. And that unique h is written as the pair fg.
Don't FG yield to 1 and yield to 2 be injective though?
No. F and G are definitely not necessarily injective. We could have had here any. This discussion didn't assume that K is necessarily of bigger cardinality than N or M. It could have been given a singleton set. Then F and G would have never been injected.
Yeah.
Unless N was or N was empty. Now I've ran out of space to show the other notion of multiplication, but I've also run out of time.